My name is Larry Denneau, and I'm with the University of Hawaii at Manoa in Honolulu. And I'm over here on Maui today to service our telescope on Haleakala tomorrow. And what our telescope does is it searches for hazardous asteroids, so asteroids that pose a threat to the Earth. Our project is called ATLAS, and the telescope we have here is one of 4 telescopes that participate in a network of telescopes that all search the sky for hazardous asteroids. So our 4 telescopes were 100% funded by NASA for this mission. And our project at the University of Hawaii manages these 4 telescopes, coordinates observations, reduces the data in real time, and sends observations of candidate hazardous asteroids to the IAU Minor Planet Center, where those asteroids are then followed up for further observations. So we're one of several NASA-funded planetary defense missions, as we call ourselves. And we're unique in that we are able to cover the entire dark sky from the North Pole to the South Pole almost every night with our 4 telescopes. So it's becoming less and less likely that a hazardous asteroid will make it through the net and arrive at the Earth undetected. The concept for ATLAS was presented in a paper in 2013, and in 2015 NASA funded us to build 2 telescopes as a demonstration of the concept. And the 2 telescopes are here in Hawaii. So one is on Haleakala, just up the road, and the other is on the Big Island of Hawaii on the active volcano Mauna Loa. So those are the 2 telescopes that NASA funded us to build initially. A couple of years ago, we were funded to build 2 more in the southern hemisphere. One is in Chile, and the other is in South Africa. And those 4 telescopes, since they're scattered across the globe longitudinally and latitudinally, let us now see the entire dark sky. And so what we try to do is each night, one of the telescopes will scan the sky in a band of the dark sky that is assigned to it for that night. And we look for things moving slowly across the sky that have signatures of being of an asteroid, but not a regular main belt asteroid. So these are asteroids that have unusual motion, and most of those are likely to be asteroids that are close to the Earth. And so when we find one, we send the observations immediately to the Minor Planet Center, where other telescopes that specialize in follow-up can continue observing those asteroids. ATLAS is what it does that's different from other telescopes is that it sees a very wide field of view in each image. So our job is really to survey the sky. When we find something interesting, we send our 4 observations that we get usually when we first see it, and other telescopes that are better suited for that job then follow it up, and we go back to surveying for more new things. Normally, the telescopes just divide the sky up pretty evenly, and each telescope covers that patch of sky. But when one telescope finds something interesting, we know that if that object is not followed up or continued to be observed, it could get lost because the motion could be unpredictable enough that a day later it might be difficult for another telescope to find. And so our telescopes are able to, when we find something that has a motion that suggests that it has a good chance of getting lost if it's not followed up immediately, we can hand that object off to another ATLAS telescope that's about to observe. And as long as it's on a part of the sky that another telescope can observe, we'll continue to observe it. Eventually, it'll be followed up by follow-up telescopes that are dedicated to that job, because the orbit has been improved enough that they know where to find it the next night and the night after that. But until then, we can continue to observe it because we have a very wide field of view. And even though we don't know precisely where the asteroid is on the sky, we can catch it with our large field of view. We keep all of our exposures, so we're now up to about 2.5 million exposures taken across all of the telescopes. Each single exposure is about 200 megabytes each file. And so the size of our data is already over a petabyte. But all of that data is preserved so that we can go back to old data and look for asteroids that might have been in old exposures, when we just find them. And also in our exposures, there are many stars and galaxies that are of interest to the other remaining astronomical community who cares about stars and galaxies. And so The ATLAS data not only is useful for finding hazardous asteroids, but can provide a huge value to other astronomers because of the other kinds of things that we see and measure and record in our own database. My background, actually, before I became an astronomer, was in engineering, and I've known many astronomers and engineers over the years who've worked with the project or worked related to the project. And it's taken so long for JWST to launch that it was very scary when it launched. I think everybody who was remotely interested in it was on the edge of their seat when it launched, because so many decades of work by many people went into it, and it was just very scary to you really we're rooting for it to get up there. But from an engineering point of view, it's just been this incredible feat that's been executed. Scientifically, what JWST does JWST will not have the impact in planetary science that it will have in cosmology and extragalactic astronomy. But there are things that it can do for solar system science that no other telescope will definitely be able to do. And that's because it observes in the infrared. And a common problem from Earth for projects like ATLAS is that when we see an asteroid, we don't know, it's very hard for us to tell or to disambiguate the size versus the reflectivity. So a very reflective asteroid looks bright, but also a very big asteroid will look bright, and sometimes you don't know which it is. By observing in the infrared, like JWST can, they can resolve that disambiguity very quickly, right, or immediately, because they're able to measure the heat coming from the asteroid. So that tells us how large the asteroid is. And so for the things that JWST will be able to see, knowing the size very specifically and very soon will let us understand a lot of surface properties of these asteroids in great detail. As far as impact for planetary defense specifically, I couldn't give you a good answer for what the impact will be from JWST. I'm sure there will be an impact somewhere, but right now it's pretty early to understand how it might impact our field. Planetary defense is, so what that means is protecting the Earth from hazardous asteroids or possibly a comet impact. We've gotten a boost this year because of this movie, Don't Look Up, that came out last year, and it's generated a lot of press and interesting kinds of questions. And a lot of that movie actually is very similar to how our field operates. But the risk is out there, and projects like ATLAS and Pan-STARRS and Catalina Sky Survey, and there are some projects in Europe that are getting started to also participate in planetary defense in a larger way. All of these efforts, please support them and help us save the world from asteroid impacts.